The next two videos will be devoted to a brief introduction of the so-called finite element method, which is FEM. For the same equation that we have studied the finite difference method for, which is negative U double prime is equal to F, and we'll make it simple and assume it is the boundary conditions are zero, meaning another way to say that is homogeneous boundary condition. And for us to talk about finite element, we would have to rewrite the problem in a so-called variational form. In this video, we're going to show that this equation is equivalent to the variational form and another form called minimization problem. All right. And next video, we're going to discretize the variational form, which leads to the finite element method. So for notation purpose, I'm going to call this problem as D. I'm calling this problem as D. The problem in this form as D. And I'm going to define a space, okay, a space W to be a space of functions V, all the functions V, which goes from 0, 1 to the real line, so a real valued function. And I'm going to assume V is continuous, and also V prime is piecewise continuous. Okay, and we assume V0 is equal to V1 is equal to 0. So that's a space W. Okay, the so-called variational form, you soon see why we're defining this, but this would be a starting point for us to derive the finite element method. That's why we need to do it now. That form is find a function U in the space W, right? There are infinitely many functions in the space W. Find the one such that I'm going to introduce the notation like the inner product for vectors, parenthesis U prime V prime is equal to F V. Okay, and this is true for any. This notation is for any V in the function W. Okay. So we're going to call this problem V. So V for variation is variational form, right? And this notation is you think of this as an inner product of functions. This definition is like if you give me two functions, W1, W2, the inner product is defined to be you multiply them together and integrate it from 0 to 1 dx. Okay? The third problem, which is interesting, is that this equation is actually equivalent to a minimization problem, which is you find U in the space W such that if we define a functional FV, a functional is a function. You give me function V, I calculate it according to this and get a number, the function of functions, 1/2 V prime minus FV. All right. If we define such functional, capital F of V, we have Fu is less than or equal to Fv for any V in the space W. Okay? In other words, U minimizes this functional. So U minimizes this functional F. Okay? So for D, U is a solution for that differential equation. Here, U is a minimizer of this functional. If you change V, this functional, if you change V has different value, but it goes through all the V's and find the V that minimizes this. That would be the solution U, right? We're going to call this minimization problem. Okay? So we have D, we have V, we have M. Problem D, problem V, problem M. Okay. So the mu is minimized. Another way a neat way to write this mathematically is that U is the argmean when you go through the argmean when you go through all the W space of FV. All right. So the argument that minimizes this. So as an example, if we have the function, so this is function x squared, okay, x squared, xy. So the argmean of x squared, x minus 1 to make it more interesting. We go through all the x, all right? So I'm going to raise this above. So this is x squared minus 1, okay? Minus 1. So the argmean means that the location of the number x that minimizes this function, we can clearly see the quadratic function. So is this location is where the function takes the minimum value. So the argument that give you the minimum value of the function is 0. Okay, that's x. The x that attains the minimum value of x squared minus 1. All right. This is different from if I'm asking you the minimum possible value of x squared minus 1 by going through all the x. That's of course negative 1. You plug in 0. Okay. That's what the argmean is. So what we're going to do next is that in the calculus setting, if you're talking about U double prime, U has to be a function in so-called C2, right? This notation is in C2, 0, 1. So which is a function of this is twice differentiable. You take a function in it, you can differentiate twice. You get a meaningful function in calculus, your calculus sense. So what we're going to show next is that all those three seemingly very different problems are equivalent. So for U in C2, we can show problem D is equivalent with problem V. Problem V is equivalent with problem M. All right, that's what we're going to prove. Okay. So we're going to go from, we show once you have D, you have V. So what do we need to prove when we try to establish that is that if U satisfies problem D, then U satisfies problem V. All right, that's what essentially we need to prove. That is, if you use a solution of the equation, which is if you solve this negative u double prime is equal to f, okay, and u0 is equal to u1 is equal to 0. Okay. Now what do we have is that you can multiply. So if you tell me negative v double prime is equal to f, I can multiply both sides by v. That's still equal, right? That's still equal. And I can take this v. This is any function in the space W. Okay, space W. It was equal. I multiply by the same guy. Is still equal. The next step is that after I multiply, I integrate. From 0 to 1. That's still equal, because if the two functions are equal, I integrate them. They must be equal as well. Okay. The magic here is that something called integration by parts. So what we do is we have 0, 1, u double prime v. Okay, this is the way to do it. One way to write down the integration by parts is this is v, this is u double prime dx, this is v du prime. Or you can use your way of doing the integration by parts. I don't really care. But this is the boundary part, which is negative v u prime between 0 and 1. Minus minus becomes plus 0 to 1 of your u prime, then you put derivative on v, right? V prime dx. Okay. This is actually equal to 0 to 1 u prime v prime dx. Because the reason is that this guy is 0, because v0 is equal to v1 is equal to 0. Okay, so that term goes away. So by our parenthesis notation, this is parenthesis u prime v prime. Okay, and what we had above, the right hand side f times v, that's a parenthesis fv. So we have just proved that. So we have u prime v prime is equal to fv. That is, u is a solution of problem v, right? So we're done. So we're done of proving from D to V. Again, V would be our starting point for implementing, for designing the so-called finite element method. The next step is, what about M? What about M? Right? What about M? We're going to show that once U satisfies V, U satisfies M. So that is, well, if U prime V prime is equal to FV for any V in the space W, then we need to show it satisfies M. What's that? We need to show if you plug in U into the functional F, is less than or equal to, it is a minimizer of this functional. So that solution to V, if you plug into the F functional, it will be less than or equal to any other F value for any VW. That's essentially the problem M statement. Okay, problem M statement. So U is fixed. It is a solution to V. We cannot do anything about U. But let's look at F of V. So F of V, this is, we know by the definition of the F, that's 1/2 V prime minus F of F in the product with a V. Okay. And if we define V, if you take the difference, so we take the difference between U and V. So V is U plus W. Okay, U plus W. And then what do we get? We have 1/2. The parentheses again means integration. So it's u prime plus w prime, u prime plus w prime, minus f is u plus w. Okay, plus w. And by rewrite this is we know this is the square, right? The square, the integrate. So this is 1/2 u prime, okay, and then you have u prime w prime, another u prime w prime divided by 2, so you get u prime w prime plus 1/2 w prime, okay, minus fu minus fw, right, minus fw. So if you look at this, okay, this two term is 0. The reason is that is a result of, so you solves problem V, the V statement above, as we had here, right? So we know that u prime w prime is actually equal to fw, right? Fw, because that was true for any v. In particular, you take v to be this w, which means u prime w prime minus fw is equal to 0. So these two terms is 0. Okay, so we know fv is equal to fu, right? Fu, what is fu? Fu is these two terms, right? Fu, then as two terms go to 0 plus 1/2 w prime. Okay. This is larger than or equal to f of u. The reason is that 1/2 w prime. Remember, the parenthesis notation is the integration. So it's integral from 0 to 1 of w prime squared dx. You're integrating a square function, so that's always non-negative. Okay, that's always non-negative, because you're integrating something which is non-negative. So there you go. We showed fv is larger than or equal to fu. So the u, the solution to v is the minimizer of this functional. All right. Next, we prove that problem M leads to problem V. So for that we have that u solve the minimization problem. That is, u is argmin of any v in the space capital W, f of v, right? That's what we know, and we want to show that u prime with any w prime is equal to f with w, little w for any w in the space W. Okay, that's V. So that's problem M, that's problem V. Okay, so a little standard technique, which is from the calculus. If you are at a minimization point or maximization point, the derivative of the function is equal to 0. So for that, we basically look around. You have u, I look around the u, I add u, I perturb u, so I add a little epsilon small times any w, all right? I look at this guy, okay? And this is for any w, this is a function of epsilon, okay? So we define that of g of epsilon. So what is that? By definition of f, we know that's 1/2 u plus epsilon w prime and then u plus epsilon w prime minus f u plus epsilon w. If you expand it, you see that that's 1/2 u prime, and then epsilon w prime u prime. You have two of them. First we minus f of u, and then for the 2 times 1/2 you get 1. So you have epsilon u prime w prime, right? Minus epsilon f w, okay, and then plus 1/2 epsilon squared w prime. So we have this term comes here, this term comes here, right? And then we do foiling on the u plus epsilon w. Okay, so this function of epsilon, and again, we need to take the derivative, right? We need to look at the derivative. The derivative g prime epsilon. Okay, now it's function of epsilon, so you take everything else as constant. If you differentiate it, you get u prime w prime, right? Minus fw, that's the epsilon term, plus 1/2 epsilon squared becomes 2 epsilon times 1/2 becomes 1 epsilon times w prime. Okay, so the u is a minimization point. U corresponds to epsilon equal to 0. This means that the derivative at 0 must be 0. Okay, calculus. But g prime 0, we know g prime epsilon. You plug in 0 for epsilon, you get is u prime w prime minus fw. So that's 0, which means u prime w prime is equal to fw for any w in the space w. Okay, so that's v that we want. So we showed m leads to v leads to m. So we know v and m are equivalent. We started by showing d leads to v, so we only need to show v leads to d. V leads to D, problem V leads to problem D. So if U satisfies the variational form, then you solve the equation, okay? Which is if U prime V prime is equal to F of V for any little v in the space W, then negative U double prime is equal to F, okay? Trick here is again integration by parts. So we know that u prime v prime is equal to, by definition, is the integral of u prime v prime product. Okay, so this is, if you do integration by parts, is u prime times v for the difference of 0 and 1 minus 0 to 1 u double prime v dx. Well, given v is in the space W, we know this is just equal to negative from 0 to 1 u double prime v dx. And well, from the assumption, we know this is equal to f of v. So if you look at the starting guy and the end guy, we know that if you put them together, we know this is 0 to 1 of negative u double prime minus f, this whole thing times v dx equals 0. Okay, this is true for any v in W. Okay, and a little bit of more fine analysis, which we're not doing here, means that in that case, if that's true for any v, so you can basically take v to be something very close to negative u double prime minus f. So you get this function squared, okay? So it turns out you're integrating a square. This guy must be 0 if the integral of the square is 0. So U prime minus F double prime minus mass must be 0, which means negative U double prime is equal to F. So the proof is a little more involved. Basically, if you assume negative U double prime is not equal to F for on a little interval, then you can make a V to be equal to that guy on that interval and outside 0. Okay, so you can see then the integral becomes the square on that part. That part must be 0, which leads to contradiction. Anyway, so we have come from the equation D to the variational form V to the minimization problem M. The minimization problem will give us a lot of analytical tools, which we're not going to rely on. We're not going to talk about in any details in this course. In fact, this FEM part is not really required for 362, but it's actually very important scheme to at least for you to understand a little bit basics, and we'll show that which this method actually leads to finite difference schemes that we have done already. A special case of this leads to the finite difference we did. So it's quite interesting to see the connection. Okay, so we are basically saying that the FEM is starts from the problem V, which states that, well, I need to find U in W such that U prime V prime is equal to FV. This is true for any V in the space W. Okay? We still need to argue that the solution is unique. So the uniqueness of the solution, this you can prove by contradiction. So if you assume U1, you get U1, U2, they are both in the space W, and they're both solutions. Which is to say, you have U1 prime V prime is equal to FV, and you have U2 prime V prime is equal to FV. Okay, this is true for any V in W, any V in W. What you do is then you subtract one equation from the next. You get U prime minus U1 prime minus U2 prime V prime is equal to 0. Okay, so this is true for any V in W. In particular, we can take V to be U1 minus U2 because that's still in W. So we get that this integral from 0 to 1 of U1 prime minus U2 prime squared dx is equal to 0. Okay, so that means my U1 prime minus U2 prime must be 0. Okay, and which means, because that's U1 minus U2, the whole thing prime, which means U1 minus U2 is some constant. But we know at the boundary, U1 minus U2, the whole function at 0 is 0. So the whole thing is a constant. We know the value at one point, which means U1 minus U2 must be 0 everywhere. So U1 is identical to U2. The two conditions are the same. That means there's only one condition. There's only one solution. Okay? So what's next is that we're going to discretize the space. So we're going to, which I will leave to the next video, discretize space W by some WH. Okay, and and then we come up with something called basis. Basis for WH, and then the matrix vector for what we have in V, in problem V, for U prime, V prime, and FV thing, okay? And for them to be the same, we arrive at an equation, which you will see for a particular case, which we're going to again do next in the next video. For a particular case is identical to the finite difference matrix, -1 to -1. All right.